Okay, in this video we're going to look at efficiency and power. We might split it into two if time goes a little bit long, but we'll see how it goes. Okay, so first of all, power as a measurement. So power is equal to the amount of work done per unit time. Okay, so the amount of work done. Now remember our definition of work done: force times the distance moved in the direction of that force. Go back and watch that video if you need a reminder. So power is the amount of work done per time. So that's in joules, that's in seconds. So you imagine the unit of power to be joules per second. Another name for a joule per second is a watt. Okay, so a watt is the unit of power in this case. Now you will have come across watts before at GCSE, you will have come across kilowatts as well. Kilowatts, remember, is just kilos prefix times 10 to the 3, so you just use that as needed if it comes up. Right, so that's your basic understanding of what power is, but let's look at a situation where we need to work out power. So I've got a car going up a hill, and it's going at a constant speed of 12 meters per second. Now, it's moving at a constant speed, so you should be able to tell me something about the forces here. Well done if you can tell me that they are both equal, so the force going up in this direction must equal the force going down. So if we know the weight, which we just happen to do, the weight of the car is 10 kilonewtons. So the weight of the car is 10 kilonewtons. Now bear in mind that weight is acting down there. So we need to know an angle. It's not going to give you an angle, we're going to say it's at 20 degrees. So, well, my first point of call is to work out what the force down the slope is, because what the force down the slope is what the force upwards is. So let's do that. So we've got a situation where we've got our weight acting downwards, so we can create our nice vector triangle as we've done in previous videos. So that represents the 10 kilonewtons, and we've got an angle here which would be 20 degrees based on the geometry of what we'd see, and we're looking for the weight down the slope, which is this force here. So well done if you've already rushed ahead and got it, but I'll do it anyway. So we're using sine here, sine theta is equal to opposite over hypotenuse. So in this case, we'll rearrange this quickly to be sine 20 times by 10 times 10 to the 3. Okay, 10 times 10 to the 3 because it's 10 kilonewtons. And that gives us, I'll work it out my calculator. Three, 4, 2, 0. 3, 4, 2, 0. Okay, so we've got 3, 4, 2, 0 newtons acting down the slope. If you found understanding of that trig difficult, do go back, watch some of the earlier videos to get yourself happy with vector resolution and whatnot. So we've got 3,420 newtons acting down the slope. That means that the force produced by the car going up the slope must be 3,420 newtons. It's got to be because it's moving at a constant speed. Now my question is, what is the power developed by the car in order to do this? So the car is putting an amount of energy in per second to allow it to have a force to allow it to move, isn't it? So we need to work out what the power of this car is from the information that we've been given. Well, we've been given a velocity, and we now know the force that needs to be there in order to maintain that balance and keep moving at a constant speed. So, what do we look to do? Well, we need to derive a term or an equation to allow us to work out power. Well, we've already suggested that power is work done over time. And from the questions we've done before, remember that work done is equal to a force times distance travelled in the direction of that force. So, what we can do is we can rearrange this for work done, which means that work done in this case equals power times time. And what I'm going to do is I'm going to insert that into this equation. So I'm going to end up with P times T is equal to F times D. Then finally I can rearrange this to P equals F times D divided by T. And that's a nice equation. But there's a few issues here. We're not given D or T. But if we look very carefully here, what you might see is that D divided by T is distance over time. Distance over time is velocity. So we can change this to read power is equal to F times V. And that equation is the one I'm going to use here because I've been given the force, I've got the velocity, all I need to do now is work out the power developed in this instance. So we times the two values together, so we've got 12 times 3420. So because power is equal to force times velocity, then power will be equal to 3420 times by 12. I can't do that in my head. 41040. 41040 watts. Now, we might want to suggest a better unit for this, so we'd probably say 41 kilowatts. Okay, so that's the equations you need to be starting with. So, for power, these are in your equation sheet. You've got power equals work done over time in watts. We've also worked out power developed, say, in a car, force times velocity when moving at a constant speed. Obviously, if we've got a changing speed, then we've got a changing power. It's not going to work. So, have a look at that. Have a go at some examples in your textbook, and we'll move on in the next video to efficiency, specifically around this example.